Problem 8.18. Determine the convergence radius of the following power series and specify the interval when they converge absolutely. Okay? So, if you remember from the lectures, the convergence radius is the interval for which this series converge absolutely, right? And in order to test that, we usually use the root test or the quotient test. Okay, so let me get like this. So the sum from n equals 1 to infinity of x to the n times 2 to the n squared, right? If we want this to converge, to be convergent, what we can try is the root test, right? And the root test, if you remember for series, says that the limit when n goes to infinity of the nth root of a sub n, and this is the a sub n right here, has to be smaller than 1, right? So in this case, the limit when n goes to infinity of the nth root of this, so this is x divided by 2, the nth root of n squared, but this is going to be the absolute value of this, right? The limit of this is going to be 1, so this has to be smaller than 1. This means that x, the absolute value of x, has to be smaller than 2. Okay, so that implies that the series is convergent. Series is convergent in -2, 2, right? And now in the extrema, we need to of the interval, what it means in this case is 2. We need to test it case by case. So in this case, we have what happens at x equals 2, the absolute value of x equals 2. We want to see if it converges absolutely. So yeah, in other words, this is like this, right? So the absolute value of this is 2 to the n divided by 2 to the n times n squared. This is the series. So this is the same as the sum from n equals 1 to infinity of 1 over n squared. And we know that this is convergent. So this series is convergent in -2, 2. Absolutely convergent in -2, 2. Okay? Another way to do this is see that because this is going to always be x to the n, this is going to be convergent in the radius rho, which is the limit when n goes to infinity of the nth root of 1 over whatever is multiplying x sub n, right? X to the n. So if we have a sub n x to the n, this is 1 over this, okay? And so in this case, the absolute value of this, right? And so the radius of this is the limit when n goes to infinity of the nth root of 1 over this. So this is 2 to the n squared. The limit of this is 2. Okay, so this is the radius of convergence, if you want to do it like that, okay? Both ways are equally correct. Now the second, we have the limit, the sum, for n equals 1 to infinity of n factorial x to the n to the n, right? Now in this case, instead of doing the root test, I'm gonna use the quotient test. Okay. Now, for the quotient test, we know that the limit when n goes to infinity of a sub n divided by a sub n minus 1, and in this case, this is a sub n. And so this is the limit when n goes to infinity of n factorial x to the n divided by n to the n divided by n minus 1 factorial x to the n minus 1 times n minus 1 to the n minus 1. And so this is the limit when n goes to infinity of n times x divided by, and then we have n to the n, and here we have n to the n, to the n minus 1. So we subtract this, and so we have, this is the limit x times the limit when n goes to infinity of n minus 1 over n to the n minus 1. And if you compute this, this is 1 minus 1 over n, right? So this thing is 1 over e. So this is x divided by e. This has to be smaller than 1. So the series is convergent. The series is convergent in minus e. Okay, this is what the quotient test says. And obviously, sorry, I'm forgetting, because we want the interval when they converge absolutely. This is always the absolute value of all of this, right? So the absolute value of this, the absolute value of this, the absolute value of x has to be smaller than e. So that's why it converges in minus e. Okay. Now what happens when x is equal to e? Okay, x is equal to e. We need to check always the points of the interval, right? The extrema of the interval. So we have e to the n divided by n to the n. In order to check this, we need to use Stirling's approximation for the factorial. This is, remember, 2 pi n times n to the n times e to the minus n. So this term here is approximately equivalent to, if we multiply it by e to the n divided by n factorial, sorry, n to the n, we get this. So this is approximately equivalent to 2 pi n. So this is divergent, right? Because this actually doesn't converge to 0. Okay, so this is convergent in minus e open. Okay. Now let's see. For 3, we have the sum from n equals 1 to infinity of x to the n divided by n times 10 to the n minus 1. And again, let's do the root test, why not? So the root test says the limit when n goes to infinity of the nth root of this x to the n divided by n times 10 to the n minus 1, right? So this is the limit, the test for absolute convergence, and this is the limit when n goes to infinity, of the absolute value of x divided by the nth root of n is 1, and the nth root of 10 to the n minus 1 is 10. Okay, so yes, so that's not the limit, that's already the limit computed, and this has to be smaller than 1. So the series is convergent in minus 10, 10. And now we have to check what happens when x is 10, when the absolute value of x is 10, sorry. So then we have 10 to the n divided by 10, we have 10 over n. This is infinity because this is a multiple of the harmonic series. So this is just convergent in minus 10, 10, absolutely convergent in minus 10, 10. Okay? Now we have part 4. The sum from n equals 1 to infinity of x to the n divided by the square root of n. Now if you compute either the quotient test or the root test, right, you will get the limit when n goes to infinity of the nth root of the square root of x to the n divided by the square root of n, and the limit of this is x divided by 1. This has to be smaller than 1, sorry, the absolute value. So then x has to be in minus 1, 1 in order for it to be convergent. What happens when when the absolute value of x is 1? Then we have 1 divided by the square root of n, and we know that this is convergent. Sorry, divergent. So this convergent, absolute convergent in minus 1, 1. Okay. Let's do part 4. The sum from n equals 0 to infinity of 3 minus 2x to the n. The root test is the limit when n goes to infinity of the nth root of the absolute value 3 to minus 2x to the n, or in other words, this has to be 3, the absolute value of 3 minus 2x has to be smaller than 1. Okay, so in other words, that this says that 3 minus 2x has to be between 1 and minus 1, and so if we subtract, let's see, it's, wait a minute, is 4, right? So this is 4 smaller than minus 3 and smaller than minus 2, and we divide by minus 2, so this is 2 greater than x greater than minus 1. Is that true? Sorry, this is minus 4, so this is plus 1, yes. So x has to be between 1 and 2. Okay, now what happens in the extrema of this interval? What happens if x is equal to 1, for instance? We have sum from 3 minus 2, 1 to the n. This is obviously infinity. Okay, so the series is divergent at the extrema of this interval, right? Because if x is equal to 2, the sum is from n equals to infinity of minus 1 to the n. But the series of the absolute values of this is the same as this. So this is absolutely divergent. So the convergence here is in 1, 2. Okay? Now let's do the last one, which is part 6. Is the sum from n equals 1 to infinity of x minus 2 to the n divided by the square root of 2n. Now the root test, you see where this is going. This is the limit when n goes to infinity of the nth root of x minus 2 to the n divided by the square root of 2n. And here this limit is going to be x minus 2, right? The absolute value of x minus 2 has to be smaller than 1. So that means that x minus 2 has to be between minus 1 and 1. If you sum 2 to both sides, you have 1 between x and 3. So if x has to be in this interval, what happens if x takes the value 3, for instance? You get the sum from n equals 1 to infinity of 1 divided by the square root of 2n. We know that this is divergent. If x is equal to 1, this is the alternating series, but the absolute convergence is the same, so this convergence is between 1 and 3.